So if you own a battery asset, you might want to have a look at power quality. If you want this thing to last you 20, 30, 40 years, why does power quality, so the smoothness of that curve, the quality of the power, why does that matter so much when we're talking about batteries?
It's becoming a bigger issue as we have more inverter-based technologies connected to the network, and the standards are changing to keep track of that.
A bit like noise cancelling headphones.
Yeah,
rather
exactly.
than you can't have this conversation without thinking about high-end audio. I don't think.
Yeah.
Anyway.
No, yeah. Noise cancelling headphones are a perfect one because effectively they're listening to the noise that's not your music and they're injecting the opposite.
Hello everybody, Quentin here. This week we're talking about a niche subject and it's a bit technical, but it's worth bearing with us. We're talking to Tim Rastall from Enspec about power quality. Now, this is a thing that doesn't really matter until it does. Until it's a problem, you don't really think about it. Power quality is really important to developers and asset owners and operators, or anyone who's connecting to the grid. So in this conversation, we unpack what it is, why it matters, and what you can do about it. We hope you like this conversation, and do let us know what you think in the comments, and hit the subscribe button. It means the world to us. All right, Tim, what is power quality?
So power quality is effectively the measure of abnormalities in power quality metrics. So that's voltage, current, and power flows. We're basically looking how abnormal or how perfect are those kind of different signals in relation to how they should be.
Okay, so power quality is how... Basically, it is what it says on the tin.
Yeah.
What quality is the power? You don't really think about this, right? The
No.
power that's running around the transmission system or the distribution system, there is different levels of quality of that power and of the signal and all that stuff. And today we're talking about the quality of the power. Mm-hmm. It's not just there or not.
No.
There's a few bits to it. And the reason why we're talking about power quality today on this podcast, and it's a pretty niche thing to go through. To set the scene, power quality it comes up in lots of conversations. If you're trying to build a battery or a wind farm or a solar project and you're speaking to the network operator or you're connecting to a private wire or you're installing a transformer, if you're building and operating these assets, power quality does actually come up in conversations a lot because all of the folks that you're connected to, they want to make sure that the quality of your power meets their requirements. And there's loads of downstream issues if it doesn't. And so the why we're doing this conversation is to talk through with an expert, you, Tim, who you spent your whole career so far working in power quality. So I can't think of anyone else better to do this with. We want to know, what is this thing? What should we be thinking about around it? And what's the impact? Mm-hmm. So, okay, Tim, let's talk basics right now. So let's talk about power as a wave. Let's get that thing done, which is the basics before we move on to what power quality is. So power is a sine wave going from positive to negative to positive to negative. What can you describe that?
Yeah, so you have voltage and you have current. They basically alternate at 50 hertz, so they're repeating 50 times every second. They have a positive peak and then a negative peak, and then they repeat again and again and again and again, and 50 times every second.
This is all power. You plug your iPhone in, you've got a big motor, you turn the lights on. This is all 50 hertz. It's all happening 50 times a second. Positive, negative, positive, negative, positive, negative.
Yeah, that's correct. In the alternating current grid in the UK, other kind of countries may have 60 hertz systems, but in the UK it's 50 hertz system.
Okay, and keeping the grid at 50 hertz, that's why we have frequency response like dynamic containment and FFR. Mm-hmm. So I think folks probably understand the frequency side on that world, but then there's the quality and how smooth the transition from positive to negative and positive to negative bit is. And that's where you guys come in.
Yeah.
So let's talk about batteries now. Why does power quality, so the smoothness of that curve, the quality of the power, why does that matter so much when we're talking about batteries?
So when you look at a battery, it's got a DC generation. You then use an inverter which chops up that DC signal very high frequency, and then it outputs it through an output filter that smooths it back to that 50 hertz sine wave that we've just discussed. You can't have that be perfect in an inverter system, and you still have some components of that high frequency switching that come out in the output signal. So you have the 50 hertz signal, but you also have overlaid on that kind of multiples of that 50 hertz system. So you have like the fifth multiple, which is basically 5 times 50 hertz, 250 hertz, overlaid on that waveform that basically lead to little distortions all on the wave if you were to look at it. That's an issue because they kind of contribute to total harmonic distortion, which is THD. And that is limited by the network, the DNO operator, the transmission operator, in terms of the level of THD that you can create on the electrical system.
Okay, one step back, one step at a time. So a battery cell produces power, and you put that through an inverter at a battery grid scale battery site, and the inverter chops up that power and turns it into a sine wave.
Yeah.
And that inverter, in the process of going from DC to AC, you create a whole load of noise.
Yeah.
So if you think about a record, a vinyl record, it's like having a load of dust on top of the vinyl. Why am I talking about vinyl records? No one, you can't really do it with MP3s. If you think about a piece of music and you've got some dodgy speakers, right? You're adding in a bit of the noise. And the noise, it contributes to a load of issues later. It's really difficult to have this conversation without talking about playing guitar or vinyl records, or what are the other examples? Anyway, so, and it's that noise that we're worried about, the noise in the signal. Okay, you talked about harmonics before. Harmonics sound very exciting. They sound, beautiful sounds. But in power systems, harmonics are bad. Is that right?
Yeah.
We don't want harmonics.
Yeah. I mean, they're all called harmonics, even the fundamental 50 hertz. That's first harmonic. That's the one we want. That's the power that we want to provide. And then you have multiples of that harmonic all the way up to the 100th harmonic that we look at. So that's 5 kilohertz and 5,000 hertz. Effectively, there are limits to every other harmonic order, and the site cannot cause the harmonics at that connection point to go over those limits, because we start to see issues with telecommunications, overheating of cables, the damaging of transformers. It just creates all sorts of problems on the network.
So we want, when we go through our inverter and we can connect to the grid, we want the 50 hertz, but we don't want all the multiples of that. We don't want the 250 or the 500 or 1,000.
Correct.
We just want the 50 hertz, and we need to filter those bits out. Okay. Can I ask you, it's probably a very basic question, but are some batteries better at this than others?
Yes.
And what's that about? Is it about the equipment you choose or the quality? Is it about, if you spend more money, do you get less harmonics? And does that mean the grid is happier about you connecting? Or how does that work?
Yeah, so there is that component. So on the inverter modules, they can have different levels. So they can have different switching stages, sort of one switching stage up to a lot of different switching stages. Or they can switch at different frequencies. So they switch between 20 kilohertz to 50 kilohertz. And obviously that switching frequency changes the harmonic spectrum that's coming then out of the output inverter. So depending on the inverter that you've chosen, how well it's been designed, the output filter, you can have different levels of harmonic contribution. And effectively, when we're looking at a new site, we will get that information from the inverter manufacturer. They will say, this is our inverter, this is the harmonic spectrum that you'll see across all the different output power levels. And we'll then assess that and see if the end result creates an issue. Now, it's not only the inverter. Effectively, the inverters are injecting harmonic currents when they're doing their job. Those harmonic currents, if you go back to Ohm's law, which is voltage equals current times resistance, it's kind of one of the fundamental equations in electrical theory. When you have a current, it basically multiplies by the resistance to give you a resultant voltage. So if you're injecting those currents out of your inverter and there is no resistance at those harmonic orders, you don't have an issue because it's not generating a voltage. However, if you have high impedances at certain harmonic orders, so one of the big ones is the fifth harmonic order. If you have a high impedance there and you're injecting current at the fifth harmonic order, you result in a high harmonic voltage, and that's the one we're looking for. That's the one that's going to create bad power quality issues. So it can be the inverter, it can be an unlucky connection that has bad impedance profile, or it can be a conjunction of the two.
So if I want to build a battery and I want to connect to the grid, and the engineer at the grid is saying, "Oh, we'll give you a connection, but you've got to meet these stringent requirements."
Yeah.
I'm not an engineer, right? So I need to go out to the market and go to Enspec and say, help me.
Yeah.
What do you guys come and do? What's the service I get?
Okay, so effectively, you've got an idea of where you want to connect and the site size and design that you want to use, the equipment manufacturers. You provide us with the details of that site, a single line diagram showing your connection point, your transformers, your battery inverters. You provide us all the data sheets. We then stick that into a model. So we build a simulation that represents the site in a computer. And we effectively look at the site's operation for certain power quality metrics in relation to the standards. So when it comes to the harmonic standard, we model the site inverter harmonic contribution. We model the network connection impedance profile, which is provided by the distribution network operator that you're looking to connect to. And we effectively simulate that site in operation, and it results in a resultant harmonic THD. Total harmonic distortion, that we then check against the standards to say, yes, you can connect directly, or no, you need to do something.
So you look at the site, the grid operator gives you some information, we give you some information, you stick all that in a model, and you come out and say, you're going to have some problems or you're not going to have problems.
Correct.
And how important is this? Because for asset owners building battery assets, surely there's loads of batteries built in the UK and they haven't had this problem. So why should anyone really care about this?
It's a condition of energizing your site when it's built and you're ready to start, using your battery system. The network operator, the DNO or the transmission operator, they will ask for the selection of these studies. One of them is the harmonic study, which is known as the ENA Energy Networks Association G5.
I remember filling out those forms back in the day.
Yeah. So effectively, it's now been coupled within ENA G99 that you basically need to do the G99 studies, and you need to provide the G55 study as well, which is a report that the DNO is going to be looking for to prove compliance and basically tick that box and say, yes, you can energize your site.
So is it getting more difficult to connect? So is it that in the past, this stuff hasn't been that important because connecting has been a bit simpler, and now the Electricity Networks Association and distribution network operators are coming together and saying, actually, we want you to pass more difficult standards, and now power quality is more important, and it's because suddenly you've got to think about it where you didn't before. Is that right?
Yeah, I mean, in this transition we're moving from rotating sources of generation to inverter-based. Inverter-based has this high frequency switching, and it creates harmonics. You don't have those same issues from traditional power generation. So the way we're moving, it creates more issues on the network. So the network now has to be more aware of that, because effectively, if they left it unchecked, the harmonics would build and build and build, and then people would start to have issues kind of all over the network. So yeah, it's becoming a bigger issue as we have more inverter-based technologies connected to the network, and the standards are changing to keep track of that.
And so one part of it is, can you connect to the network? Tick yes or tick no.
Yeah.
But then there's a bigger thing here, which is power quality can cause your whole entire site and systems to degrade, right?
Yeah.
These harmonics can cause crazy things to happen.
Yeah.
Across cables, transformers, switchgear, the whole lot. Can you talk a little bit about that?
Yeah, so what we've been talking about so far is known as the planning levels. So that's the network's levels that they will allow you to cause on the network and still connect. There are a second set of levels for harmonics which are actually higher, but they're called compatibility levels. This is effectively the level where harmonics would start to damage equipment. So equipment's not designed to have high frequency components running through it. And when you look at a transformer, if you have high harmonic loading on a transformer, the transformer gets very hot. They're designed to run at a certain temperature, but that means they're running a lot hotter. It degrades the oil, it degrades the equipment generally. The same for cables. They're not designed to have high harmonic loading, capacitors. But then also if you look at your kind of control electronics and telecommunication systems, it starts to interfere with things like that because you've just not got this perfect voltage waveform that you're dealing with.
So if you own a battery asset, you might want to have a look at power quality. If you want this thing to last you 20, 30, 40 years, not the cells, of course, but the other stuff. Which a lot of people, that's the assumption, right? That the transformers and cables and all that stuff will last a lot longer than the life of the cells. If you want that to happen, it's worth having a quick look as a minimum at power quality on your site and figuring out whether you've got a problem. Because if you deal with that early, those bits will last longer.
Yeah.
So I want to come to measurement and solving problems now. So how do you measure this thing? This it's like it's almost a conceptual idea of mathematics and harmonics on top of a sine wave. It's very difficult to get your head around, right? So all of that, how do you measure that on a site to figure out if there is a problem? And then if there is a problem, just talking about batteries now, how would you go about fixing that kind of problem?
If the site's already in existence, you would effectively go along and connect a power quality monitoring device. So we're effectively looking at where the site connects into the network. At that point, you'll have a certain voltage. Sometimes it's 33,000 volts. Sometimes it's 132,000 volts, whatever voltage you connect into the network. And you'll have what's known as a voltage transducer at that point, a VT, which effectively is that connection voltage and then a much lower voltage on the secondary winding of that device. What we do is we connect a power quality meter to the secondary side of that device, and we basically record the voltage waveform over a period of 7 days. That's normally the typical duration for harmonic compliance. And we'll then, it's difficult to get fully away from the maths. Effectively, you're doing what's called a fast Fourier transform.
Oh, yeah.
On the voltage waveform.
I remember these from university.
Yeah.
You get into there's a whole different plane of thinking and mathematics for Fourier, right?
Yeah. Effectively, you're pulling out the harmonic components, so you can see how much of it is 50 hertz, how much of it is 100 hertz, so on and so forth, in a percentage form. And it's the percentage that the limits are applied against. So, for example, you might be allowed 2% of fifth harmonic distortion. So we have the 50 hertz component, and as long as the fifth order is below 2%, then you're good to go.
So what does this look like? Is it like do you have to turn up with a big van, and connect these big high voltage things, or is it like a little box, a little computer? And you leave it plugged in for a week? I mean, what does it look like, and what does it cost?
Yeah,
so that's about an order of magnitude cost. Is it 1,000 quid? Is it 100,000? Is it 1 million? What does this thing cost?
Yeah, so it's roughly the size of a shoebox, and it's a little self-powered device with a battery. And effectively, you just connect it into you've got like your electrical room where all your metering is normally located. It's basically connected in there. These are typically just hired out for that week. So you're normally looking, depending on where you are in the country, a couple of £1,000 to have an engineer come and connect this device for a period of 7 days, download the data, and then give you a report that compares that to the planning and compatibility levels.
Okay. And then let's say I've spent £50 million on this big battery and I'm connected to the grid. I'm making good money. I'm in all the markets. I'm trading power. Everything's going great.
Yeah.
And then I get you guys in and say, I'm worried about the long-term life of this asset. And I just want to make sure the power quality thing is okay. And you come with your little shoebox and you connect it and you give us a report, and the report says you've got big power quality issues. Then what do I do?
So that's where you would move on to harmonic filters. So that's a sort of product that's applied to solve harmonic problems. You have different types of harmonic filter. Starting from the basic level, they're known as passive harmonic filters. So they're effectively just passive electrical components that we design in an enclosure that's connected to your network, which effectively absorbs the bad harmonics and means that they're not on the network. You can then move into active harmonic filters, which effectively the easiest way to think of those is just another inverter.
A bit like noise-cancelling headphones.
Yeah,
rather
exactly.
than... You can't have this conversation without thinking about high-end audio, I don't think.
Yeah.
Anyway.
No, yeah. Noise-cancelling headphones are a perfect one because effectively they're listening to the noise that's not your music, and they're injecting the opposite of that noise so that it cancels to zero. And that's effectively how an active filter works. We're looking at the harmonics. The ones that we don't want, we're injecting harmonics that are equal and opposite to those harmonics, which results in zero at those harmonic orders and a perfect 50 hertz signal. So effectively, you design either a passive or an active harmonic filter, you connect it in parallel with your site, and it deals with the harmonics and brings it down to planning or compatibility levels.
And what percentage of battery sites do you think have looked into harmonics and power quality? Do you guys work from... I've got no idea how big this thing is.
Yeah.
Are people is it commonplace to consider this stuff, or do you come in at the end, or do you come in at the start, or is everyone now talking about it, or is it still a new thing?
Yeah, I mean, so for new sites that are being built, it's always considered because you can't have that tick box from the network operator. You can't energize your site unless that box is ticked. So it's always looked at. Now, it's not always an issue. If you're in a very kind of strong area of networks, that's effectively where we had a lot of generation before. We've got very high fault levels on the network. The harmonics aren't so much of an issue. If you're connected in very remote areas, it's much more likely that you'll create a harmonic problem. And so then you would need to look into harmonic filtering.
Oh, okay, so in the UK, in Great Britain, where you are in the country and the history of that location
Yeah.
has an impact on how sensitive the grid is to harmonics. So you might find if you're in, for example, the Humber region in the northeast, where there's loads of big industry and you've got high levels of safety on top of all the transformers and all that stuff, then the grid isn't so worried about harmonics there. But if you're in the middle of nowhere, nowhere's a strong word, you're remote, then the grid infrastructure isn't so ready for you and they're more worried about harmonics. Is that right?
Yeah, effectively, you can have a much bigger impact on that electricity quality because it's a weak kind of network
Okay.
area. If you're in a strong network area, it's very difficult to affect the kind of power quality. But I mean, it can sometimes just be very unlucky. When you choose where you're going to put your site, the network operator will say, this is what the impedance looks like. So they're effectively saying, this is the resistance at the 50 hertz order, the 100 hertz order, all the way up to the 100th harmonic order. This is what it looks like. Do your harmonic study. If you're really unlucky and you have like a really high impedance at, say, the 20th harmonic order, and your inverter also injects current at the 20th harmonic order, you're going to create a 20th harmonic problem. But it might not always be the case. So it's very, very kind of random in terms of when these issues arise and when you have to solve them.
And what about other asset types? What about wind and what about solar? Because wind and solar, they've got inverters too, right?
Yeah.
So does that mean you have the same sort of problem to consider?
Yeah, no, definitely. We've been historically working heavily in the onshore wind industry. The kind of primary issue there, which can sometimes be the same for battery sites, is if you have a very long cable that's going from where your site's located to the grid connection point, that cable can also kind of instigate some harmonic problems.
Oh, the old telegrapher's equations. Those. But we're certainly not going to go down that rabbit hole right now. So onshore wind. What about offshore wind? They're struggling. Are they considering this thing as well?
Yeah, they're exactly the same. I mean, offshore wind usually connects into a much higher voltage. They're kind of usually be kind of transmission connected. So you do have a much stronger network there. You tend to have less kind of distortion. In some cases, if you connect in at 33 kV, 33,000 volts, for example, the actual harmonic levels at that location could already be too high. So effectively, you're trying to connect somewhere where the planning levels are already exceeded. So you get very little headroom, which is effectively your kind of contribution towards harmonics.
You've got to be really
so it makes it
quiet on the harmonics.
Exactly. You almost have to have a negative kind of contribution to harmonics. You have to absorb harmonics as a site. So it becomes very difficult. So that's the thing with offshore wind. They tend to have less of these issues, but they do still have the issues, and they do apply passive and active harmonic filtration as well.
So if I'm specifying, I've got £50 million to spend on the new Modo battery, and we're looking at a load of suppliers, big tier one suppliers all the way down to more cheaper suppliers or unheard of ones. How do I know? What do I look for? What's good? What's bad? What would your advice be to me if I'm specifying or buying a big battery system?
Yeah, so I mean, the kind of most basic check you can do is request the harmonic information of the inverters that you're considering. Within there, it'll basically give you all the harmonic orders, and it'll give you all of the harmonic injections at those orders. You can effectively, as a first exercise, just compare them all and see which one is injecting the lowest amount of harmonics. Obviously, you could still have an issue if you're just unlucky in terms of where you're connecting, but that's kind of step one. Step two, it's something we've actually been doing increasingly with developers, is basically doing a little bit of upfront work when you haven't actually chosen your supplier. So effectively, you can do some brief simulations using all of your potential supplier's equipment. and where you're looking to connect that network. And you can get a kind of feel for which ones might create harmonic problems or other power quality problems. And that can basically inform your decision just by doing a little bit of upfront checking and design work.
Because you kind of want, I imagine there's no free lunch, right? So if you buy rubbish, cheap stuff, I imagine you get more harmonics because there's less filtering.
Yeah.
And you buy really expensive tier 1 stuff, I'm sure they've got marvelous filtering, and it's not even it's hardly a consideration. And so what you want to do is get somewhere in between, I'd imagine, or just go with the Rolls Royce and go with one of these top suppliers and know you're safe. But so is that assumption right, that cost will have an impact? If you spend more, you get less harmonic, you get better power quality, or is it not as simple as that?
No, yeah, it can be that simple. It just kind of comes back to the fact that you can do, the best job in picking the equipment suppliers and have the lowest harmonic contribution, and then you could just have a very difficult connection point that has weird impedance levels. It's, gives you a low headroom to be able to connect, and you could still have the issues. But yeah, selecting a low harmonic inverter is a good first step to try and alleviate these problems. But it's definitely just something that it pays to look at it as early as possible. If you kind of just head down, developing the site, choosing new suppliers, building your site, and then you leave these power quality considerations till the very end, you can come up with some kind of surprises in terms of equipment, which it's not necessarily that expensive compared to the whole site, but it takes up space. Yeah. These battery sites are usually quite kind of compact, and if you now need to put down a 6 meter long container somewhere in your site to provide harmonic filtering, and you've not considered it till the very last minute, that can be tricky in terms of the project schedule. And
that's a good reference point. Okay, so if you can't connect because you can't get your harmonics down.
Yeah.
And then at the last minute, you've got to get online and you've got to buy one of these harmonic filtering things. Mm-hmm. And that is roughly, it's a big container size of thing.
Yeah.
So it's a decent chunk of size, weight, cost, resource, money to consider. And then of course you've got to buy one, and that's going to delay you and all that stuff.
Yes.
So this sounds a bit like fire safety. It's one of those things you really want to think about early. Mm-hmm. You perhaps don't need to spend a ton of money and time on it, but just a little bit to de-risk the project.
Yeah.
To make sure you're covered. Because if you the downside risk is huge. The downside risk is you're at zero. You can't connect. Mm-hmm. You're not making any money at all.
Yeah.
There's all this capex sat there doing nothing. All right, let's talk about Enspec, your company. You guys have been around for a couple of decades and you've grown really quickly. What is Enspec? What do you do? What's the background, and what do you do there?
Yeah, so we've been going since 2000. So we were originally founded by two brothers in the kind of power quality realm, originally focusing on power factor correction. But over the years, we've developed to be an all-encompassing power quality company. So, we'll do everything from the diagnosis, measurement, and solving of power quality issues. We have an engineering and consultancy office that's located in St. Helens, and then we manufacture our solutions in Washington, Tyne & Ware. We were traditionally owned by the two brothers, and we've recently gone through a management buyout process where myself and some of the other managers at the company have actually bought out the company.
Congrats, that's huge.
Thank you very much. Yeah, so
that deal's done?
Yes, that is. Yeah. So I'm now operating as the CTO for Enspec. And effectively, we're trying to push the kind of the growth of the company in all these different sectors, and basically making sure people know about power quality and helping people deal with the issues that come along with it.
And how many people are there in the company?
So we're just around 30 people currently, and we've gone through quite rapid growth in the last 2 years. The Power System Studies team, which does the modelling and these kind of things for upfront sites, and that's grown from kind of team of myself. We now have 7 engineers working in that department full-time doing power system studies for these sites that want to connect to the network.
This stuff is real proper engineering.
Yeah,
you really need to know your stuff to get this right. And there's a lot of measurement and I imagine a lot of devices and physical things to consider. I want to come to the last couple of questions. So firstly, we always give people a chance to plug. So if there's anything you're working on or you think people need to know about you or Enspec, then now's your chance. And then the last question is the most exciting one, I think, which is, what's the contrarian view? What do you guys believe that not everybody else believes?
Okay,
First one, anything you want to plug?
That's why I guess it would just be back to, you know, the main conversation in terms of power quality. It's worth considering it early. We know everything there is to know about power quality. We can help you.
Big statement, nice.
We can help you at any kind of stage throughout the project. If you're planning on building a site, if you have an existing site, if you're having issues, you know, get in contact with us. We have engineers, we have solutions. We can work with you to basically demystify power quality and help you have an asset that performs at its best and is compliant. In terms of the kind of not necessarily contrarian belief, but kind of, I guess, where we're going in this transition from standard generation through to net zero and you know, renewable technologies, I'd say from our work, there's a lot of times when you're looking for a connection and you can't get the connection because of power constraints in the area. There may be too much generation in that area, or you can't have fault contribution in the area. The switch gear from the DNO isn't rated for your kind of connections.
This is right. This is exactly the issue right now. We've got all these connection applications in, and we've got connection dates of 10 years or longer in the future.
Yeah. So I think kind of my view on that is that we need to move towards less of this yes or no, computer says no sort of mentality. We need to kind of work together with the DNOs to come up with innovative ways to connect these new sites. We're doing a number of projects where, you know, there may be a fault constraint, but there are ways around that you can engineer solutions to get around that. I mean, furthermore, in terms of power generation in a certain area, if we are able to basically have smart metering and basically look at the flows of power, there are probably certain times in the day where that network isn't actually overloaded. And if we can kind of time when people are using and generating power and coordinate that all together along with storage, I think that's going to unlock the network we've effectively got already without having to wait for all these delays to get these connections, which is we really need to move towards that net zero.
So if we're smarter about things like power quality and the way that the quality of the signals we're injecting onto the network, we can get more out of that infrastructure.
Yeah.
And maybe connect more.
Yeah, definitely.
I'd imagine that the distribution network operators or the grid folks, I imagine when they're looking at people trying to connect, there's a whole margin of safety they put in on top around fault levels and all that stuff, which I understand, because if they get it wrong and the lights go out, we're going to be really frustrated. But the question is that margin of safety appropriate? Is it too high? Probably is. And is there stuff we can do, like what you guys are working on, that can almost guarantee is a strong word, but almost guarantee that we're going to be all right, the grid's going to be okay?
Yeah.
Tim, just want to say a massive thank you for coming on. That was a fascinating conversation. I think hopefully we managed to do it without going too much into the weeds of numbers and engineering. But people will let us know in the comments, no doubt, what they thought about it. So if you're listening to this, please do like, subscribe, hit all the good buttons, and we'll see you next time.
Thank you.
Thanks, Tim.